Hello everyone, this is Bandgar SS working as Assistant Professor at Department of Physics, Teaching College, NASA. Today we have to going to discuss M.Sc second year paper 2nd Experimental Technique in Physics semester 4. Today we have to going to discuss the first topic of radiation sources and physics. So starting with the first point, electromagnetic spectrum. So electromagnetic spectrum, it is nothing but the frequency spectrum. So electromagnetic spectrum is the range all possible frequencies of electromagnetic radiation and their respective wavelengths and photon energy. So there is three parameters are intercorrelated, like as a frequency, wavelength, photon energy. All parts of the electromagnetic spectrum travel at the same speed. So here electromagnetic spectrum at the same speed, and the electromagnetic waves includes speed, frequency, amplitude, wavelength. So these are the properties of electromagnetic waves. So these four parameters are intercorrelated. The electromagnetic spectrum are typically described by any of the following three physical properties. First one is the frequency, second one is the wavelength, and third one is the photon. So here frequency is equal to speed of light upon wavelength. Then second formula, frequency is equal to energy upon h is the Planck constant, and last one is the energy is equal to Planck constant into speed of light upon wave. That is the so most of the electromagnetic energy, it is nothing but a energy or in terms of a power. So electric magnetic waves, it is nothing but a power or energy. It is transmitted in terms of power. So c is the speed of light, or all light travels at the speed 3 into 10 raised to 8 meter per second in a vacuum. And h is the Planck constant 6.62 into 10 raised to minus 34 joule per second. It is the Planck constant. The EM spectrum, the electromagnetic spectrum, is the entire range of EM waves in order of increasing frequency and decreasing frequency. So here correlation between frequency and wavelength. So relation between wavelength, frequency and energy are. So first column is the wavelength, it is in a meter, frequency it is in a hertz, and third column is the energy range, it is the joule. So when electromagnetic spectrum is generated, so that time when wavelength is shorter, then frequency is high, then energy is high, means increases, and wavelength is decreases. And second one is the wavelength is longer or increases, then frequency is lower or decreases, and energy also lower or decreases. So energy and frequency, it is the near about, or it is the same terms, it is changes with the wave. So electromagnetic waves are considered to be transfer wave because they are made up of vibrating electric and magnetic field at right angle to each other and to the direction the waves are traveling. So EM waves is the electric field and magnetic field perpendicular to each other, and that EM waves goes to the direction of propagation. So can travel in a vacuum. So EM wave here travel in a vacuum. So they do not need a medium travel at the same speed. So it travels like at the speed of light. So that is the table gives the various electromagnetic spectrum blocks, like as a radio wave, then microwave wave, infrared wave, optical visible wave, ultraviolet, X-ray and gamma ray. So these are their wavelength range, frequency range and energy. So wavelength in a meter, frequency in a hertz, and energy in a. So when we use the radio wave, so it is the wavelength is less than 0.1 meter in frequency, that is the less than 3 gigahertz, and energy range it is the less than 2 into 10 raised to minus 24. So like that, microwave, infrared, optical, ultraviolet, X-ray, and gamma. Next, so that diagram you have to clear what is the relation between the frequency, energy, and wave. So frequency and energy terms are same. Frequency and energy term are same, but wavelength are different. So there is the inversely proportional relation between frequency, and energy are same, but wavelength is the opposite. So you will get the, so that arrow indicate how to wavelength, frequency, and energy change. At the bottom of energy electromagnetic spectrum, there is the lower energy, lower frequency when the wavelength is maximum or longer wavelength, and when it is the up to electromagnetic spectrum or top of the electromagnetic spectrum, wavelength is shorter, then frequency is high and energy is high. So that diagram is clear the concept of what is the relation between frequency, energy, and wave. So here shows the electromagnetic spectrum and how to divide it into a sub waves and their frequency range, energy range, and wavelength. Now starting with the first wave, that is the radio wave radiation. So radio waves are EM waves or electromagnetic waves that have wavelengths between 1 millimeter and 100 kilometers or 3 kilohertz to the 300 megahertz in frequency. There is a wide range of subcategories contained with radio, including AM and FM radio. Radio waves can be generated by natural sources such as lightning or astronomical phenomena, or by artificial sources such as broadcast radio towers, cell phones, satellites, and radar. AM radio waves. So radio waves categorized into two waves. First one is the AM radio waves, and second one is the FM radio waves. AM means amplitude modulation radio waves, and FM means frequency modulation radio. So starting with AM radio waves, it is used to carry commercial radio signal between 540 to 600 kilohertz. So that information is carried by amplitude variation while the frequency remains constant. Second one is the FM radio waves. It is used to carry commercial radio signal between 88 and 108 megahertz. So that information carried out by frequency modulation while the signal amplitude is remain constant. So there is difference. When it is the AM, there is the amplitude modulation and frequency is constant, and when it is the FM radio waves, there is the frequency modulation and amplitude remain constant. Now it like all other electromagnetic waves, radio wave travel at the speed of light. Naturally occurring radio waves are made by lightning or by astronomical objects and are part of the black body radiation emitted by all warm objects, and artificially generated radio waves are used for fixed and mobile. The different frequency of radio waves had different propagation characters in the Earth atmosphere. Long waves may cover a part of Earth very constantly. Shorter waves can reflect off the ionosphere and travel around the world, and much shorter wavelengths bend or reflect very little and travel on a line of sight. A radio wave application are radio communication, broadcasting, radar and other navigation systems, and communication satellites, computer networks, and innumerable other application. Now, radio waves has two sources. First one is the natural and second one is the artificial sources. And it is like as an electronic device, or it is also known as the application of radio waves. So natural sources are lightning or astronomical phenomena, and artificial sources are broadcast radio towers, cell phones, satellite, radar, pager, two-way radio, television cables, cordless telephone, base unit, cordless telephone, wireless computers and their base units, wire computer, television, microwave ovens, dimmer switches, security systems, remote controls, fax machines, answering machines, CD players and other digital equipment in automobiles, ignition system in theaters, assistive listening system and devices for hearing impaired in theaters, wireless microphones, MRI, heart rate monitor and remote control. So these are the artificial sources of radio wave radiation. Now second one wave is the microwave. So microwave radiation. So microwave waves are electromagnetic waves with wavelengths ranging 1 meter to 1 millimeter. Frequency range 300 megahertz to 300 gigahertz. The microwave range of the electromagnetic spectrum is generally considered to overlap with the highest frequency, shortest wavelength radio waves. The prefix micro in microwave is not meant to suggest a wavelength in micrometer range. It indicates that microwaves are small compared to waves used in typical radio broadcast, in that they have shorter wavelength. Microwaves are the highest frequency electromagnetic waves that can be produced by current in a microscopic circuit and devices. The microwave can also be produced by atoms and molecules. They are a component of electromagnetic radiation generated by thermal agitation. The thermal agiation is the process of thermal motion of atoms and molecules in any object at a temperature above absolute zero causes them to emit and absorb radiation. The case for all EM waves, microwave travel in a vacuum at the speed of light. So microwave also travels in a vacuum at the speed of light. So microwave travels slowly by in line of sight paths. Unlike lower frequency radio waves, they do not travel as a ground waves which follows the contour of the earth or reflect off the ionosphere, that is the sky waves. The microwave, the sun also emits microwave radiation, although most of it's blocked by earth atmosphere. The cosmic microwave background radiation, that is the CMBR, is microwave radiation that permeates of all space, and its discovery supports the Big Bang theory of the origin of the universe. Since it is possible to carry more information per unit time on high frequency, microwaves are quite suitable for communication devices. Most satellite transmitted information is carried on microwaves, as are land-based long-distance transmission. A clear line of sight between transmitter and receiver is needed because of the short wavelengths involved. The microwave has the same as two sources, natural source and artificial source. The natural sources are the sun and the cosmic microwave background, and artificial sources are it like as the electronic device or application, circuits, transmission tower, radar, lasers and microwave ovens, astronomy and remote sensing radar transmitter. Microwave ovens, wireless LANs, cell phones, satellite communication, microwave radio, relay links, and numerous short-range terrestrial data links, television broadcasting, cordless phones, walkie-talkies, satellite communication, and numerous other applications. So these are the sources of microwave radiation, natural and artificial. Now, next one is the microwave radiation categorized into three parts. First one is the extremely high frequency, second one is the super high frequency, and third one is the ultra high frequency. The microwave portion of electromagnetic spectrum can be divided into three ranges listed below: high to low frequency. So it has the three different parameter: frequency, range, wavelength, and amplitude. So first one is the extremely high frequency. It is the 3 to 300 gigahertz. Wavelength is 10 to 1 millimeter. Application radio astronomy and remote. Super high frequency range 3 to 30 gigahertz, 10 to 1 centimeter. Application radar transmitter, microwave ovens, wireless LAN, satellite communication, microwave radio, relay links, and numerous short range terrestrial data links. And ultra high frequency, that frequency range 300 megahertz to 3 gigahertz, wavelength range 1 to 10 decimeter or 1 centimeter to 1 meter, and its application are television, broadcasting, cordless phones, walkie-talkie, and satellites. So these are the three types of microwave radiation. Now it again divided into two categories, that is the depending on the power. First one is the high power microwave sources and second is the low power microwave sources. So the microwave sources of the electromagnetic wave can be divided into high to low power sources from high to low frequency. So first one is the high power microwave sources. So high power microwave sources use specialized vacuum tubes to generate microwaves. So these devices operate on different principles, from low frequency vacuum tubes using the ballistic motion of electrons in a vacuum under the influence of controlling electric or magnetic fields, and include the magnet rod used in a microwave ovens, klystron, traveling wave tube, and guide. Solid state devices such as the field effect transistor, at least at lower frequency, tunnel diode, gun diode, and imband diode. So microwave sources includes the artificial devices such as circuits, transmission towers, radar, lasers, and microwave ovens. So this is the concept of the microwave sources related to the high to low power. Now next one is the microwave radiation. The devices work on the density modulated mode rather than the current modulated mode. This means that they work on the basis of clumps of electrons flying ballistic alloy through them, rather than using a continuous stream of electrons. A microwave are used by microwave ovens to heat food. Microwaves at a frequency 2.45 gigahertz are produced by accelerating electrons. The microwaves then induce an alternating electric field in the oven. Water and some other constituents of food have slightly negative charge at one end and slightly positive charge at one end, called polar molecules. The range of microwave frequency is specially selected so that the polar molecules, in trying to maintain their orientation with the electric field, absorb this energy and increase their temperature, a process called dielectric heating. Now next one is the radar, the first developed in a World War II, is a common application of microwaves by detecting and timing microwave echoes. Radar system can determine the distance to object as diverse as clouds and aircraft. A Doppler shift in the radar echo can determine the speed of car or intensity of rainstorm. Sophisticated radar systems can map the Earth and other planets. With a resolution limited by wavelength, the shorter the wavelength of any probe, the smaller the detail it is possible to observe. A maser is a device similar to a laser which amplifies light energy by stimulating photons. The maser, rather than amplifying visible light energy, amplifies the lower frequency, longer wavelength, microwaves, and radio frequency emissions. Now, infrared wave radiation. So, it is the short form IR. So IR is also EM radiation with wavelengths longer than those of visible light from 0.74 micrometer to 1 millimeter and frequency range 300 gigahertz to the 1 terahertz. Infrared lights include most of the thermal radiation emitted by objects near room temperature. Infrared light is emitted or absorbed by the molecules when they change their rotational and vibrational moments. Infrared radiation is popularly known as heat radiation. But light and electromagnetic waves of any frequency will heat surfaces that absorb them. The concept of emissivity is important in understanding the infrared emission of objects. This is a property of a surface which describes how its thermal emission deviates from the ideal of a black. So, infrared radiation can be used to remotely determine the temperature of objects. If the emissivity is known, this is termed thermography, mainly used in military industry application. The infrared portion of the spectrum can be divided into three regions in wavelengths. First one is the far infrared, second one is the mid infrared, and third one is the near infrared. So it categorized by some parameter. First one is the frequency range, that is the wavelength range, and last one is the application. So first one is the far infrared, 300 gigahertz to 30 terahertz, wavelength 1 millimeter to 100 micrometer. It is used for in a astronomy. Second one is the mid infrared, frequency range 30 to 120 terahertz, wavelength range 10 to 2.5 micrometer, very specific compound. Near infrared 120 to 400 terahertz, wavelengths to 750 to 2500 nanometer. It is used in a photography and video. So starting with the first radiation wave, infrared waves, that is the far infrared. The lower part of this range may also called as a microwave. This radiation is typically absorbed by so-called rotational modes in a gas phase molecules, by molecular motion in liquids, and by phonons in a solids. The water in Earth atmosphere absorbs so strongly in this range that is retender the atmosphere in effect opaque. However, there are certain wavelength ranges windows within the opaque range that allows partial transmission and can be used for astronomy. The wavelength range from approximately 200 micrometer up to few millimeter is often referred to as submillimeter in astronomy, reserving far infrared for wavelengths below 200 micrometer. Second one is the mid infrared hot objects, that is the black body radiators can radiate strongly in this range, and human skin at normal body temperature radiates strongly at the lower end of this range. This radiation is absorbed by the molecular vibration. There is the different atoms in a molecule vibrate around their equilibrium position. This range is sometimes called the fingerprint region, since the mid-infrared absorption spectrum of a compound is very specific for that compound. Near-infrared physical processes that are relevant for this range are similar to those for visible light. The highest frequency in this region can be detected directly by some types of photographic film and by many types of solid-state image sensor for infrared photography and video. Infrared radiation sources, detectors and applications. Sources are electronic devices, sun, many astronomical objects, warm objects like as a human skin, earth surrounding. Now next one, IR detectors. Electronic detector, heat sensitive paper, black bulb thermometer, photographic plate, solid state image sensor, earth atmosphere. Thermal detectors, bolometers, pyroelectrics, Gole cells, photonic detectors, photomultipliers, photoresistance, photodiodes. Application: detector in security lighting, remote control in TV, infrared camera on cars, heating, communication, metrology, spectroscopy, astronomy, biological and medical science, analysis of works of art, military, industrial application, medicine, night vision device, greenhouse. So these are the various factors of IR radio waves. Now, infrared detectors which depend on incident radiation into a output electrical signals. That electrical signal can be changed in resistance and photocurrent. Infrared radiation detection done by two ways. First one is the thermal detector and second one is the photonic detector. In thermal detector, the incident radiation is absorbed to change the material temperature and the resultant change in some physical properties is used to generate an electrical output. The signal does not depend upon the photonic nature of the incident radiation. Thus, thermal effects are generally wavelength dependent. Example, bolometer and photoconductor. In photon detectors, the radiation is absorbed within the material by interaction with electrons either bound to lattice atoms or to impurity atoms or with free electrons. The observed electrical output signal results from the changed electronic energy distribution. Example, photopolar. The ultraviolet visible wave radiation. It is also part of or portion of the electromagnetic spectrum. It is the visible to human eye. There is frequency range 400 to 790 terahertz and wavelength range 380 to 750 nanometer. So that visible light is produced by vibration and rotation of atoms and molecules as well as by electronic transition with atoms and molecules. We say the atoms and molecules are excited when they absorb and relax when they emit through electronic transition. The visible wavelengths pass through the optical window. The Earth atmosphere allows this region of the electromagnetic spectrum to pass through largely not attenuated. The portion of the electromagnetic spectrum is used by photosynthesis organism is called photosynthetic active region, that is the short form PAR, and correspond to solar radiation between 400 to 700 nanometer, substantially overlapping with the range of human vision. So these are the different visible colors from radiation. So first one is the violet, second one is the blue, cyan, green, yellow, orange and red, and their corresponding wavelength and frequency. So these colors are produced by the visible light of narrow band of wavelengths are called pure spectral color, and then can be delineated roughly in a wavelength as ultraviolet visible wave radiation. There is the some sources, detectors and applications. Sources are electronic devices like as LED, laser and sun, and we have to use as a detector eye, photographic film, electronic components like as a LDR, photodiode, phototransistor and solar cell, and their application like as a seeing, photography, communication like as a optical fiber, laser surgery. So ultraviolet visible waves radiation, there is the one major applications we have to do done photosynthesis. So plant like as animals have evolved to utilize and respond to parts of the electromagnetic spectrum. They are embedded in plants and many bacteria. Convert the light energy captured from the sun into chemical energy that can be used to fuel the organism activities. In plant, algae and cyanobacteria, photosynthesis use carbon dioxide and water, relaxing oxygen as a waste product. Photosynthesis is vital for all aerobic life on the earth such as human and animals. The portion of the EM spectrum used by photosynthesis organism is called photosynthetically active region PAR, and corresponding to solar radiation between 400 to 700 nanometers, substantially overlapping with the range of human vision. This is again not coincidental. The light in this region is the most plentiful to organism on the surface on earth because the sun emits about half of its luminosity in this wavelength range, and it is allowed to pass freely through the optical windows in earth atmosphere. Now the ultraviolet waves is a light of electromagnetic radiation with a wavelength shorter than the visible light. The range is the 10 nanometer to 400 nanometer and frequency 790 terahertz to the 30 petahertz. Ultraviolet light gets its name because the spectrum consists of electromagnetic waves with frequency higher than those that human identify as the color white. Most UV in non-ionizing radiation, though UV with higher energy 10 to 120 nanometer is ionized. All UV can harmful effect on biological matter such as causing cancers, with the highest energy causing the most damage. The danger posed by lower energy UV radiation is derived from the ultraviolet photons' power to alter chemical bonds in polymers, even without having enough energy to ionize. So, ultraviolet waves is categorized into three parts. First one is the ultraviolet A, ultraviolet B, and ultraviolets. So, it has the four categories. The first, their wavelength range 350 nanometer to 400 nanometer. It is the long wave, soft UV, that is soft ultraviolet, not absorbed by the ozone layer. 99% of the solar UV radiation reaching the Earth's surface is UV. Now second, ultraviolet B, it is the wavelength range 280 to 350 nanometer. It is a medium wave. Then it is the intermediate ultraviolet, mostly absorbed by the ozone layer. That one is the ultraviolet C, 100 nanometer to 280 nanometer. Second one is it is a short wave. It is a hard ultraviolet, completely absorbed by the ozone layer and atmosphere. Now, next one is the ultraviolet wave sources, detector and application. So sources are sun, gas discharge, lamps, black light, short wave ultraviolet lamps, incandescent lamps, gas discharge lamp, ultraviolet LED, ultraviolet lasers, tunable vacuum ultraviolet, that is the UV, plasma and cyclotron, sources of extreme UV, and their detectors causes fluorescence, glowing in some objects, film, photodiodes, photocathode, UV photomultipliers, spectrometers, radiometers, silicon detect applications, suntan lamp, making ions, making vitamin D, killing bacteria, water treatment plants, solar imaging, cosmetology, optoelectronic, photolithography equipment, extreme ultraviolet exposure. So these are the various factors of ultraviolet waves radiation. Now this is the ultraviolet visible detector. So this diagram shows which contains the lamp, diffraction grating, paper side, flow, cell, sample side, output data. So UV detector are most frequently used to measure components showing an absorption spectrum in the ultraviolet or visible region. A UV detector employs a deuterium discharge lamp (D2 lamp) as a light source with the wavelength of its light ranging from 190 to 380 nanometer. If components are to be detected at wavelengths longer than these, the ultraviolet visible detector is used, which employs an additional tungsten lamp, that is the W lamp. So their wavelength range 380 to 900. And now next one detector is the photomultiplier. So the photomultiplier, see, there is the one anode, dianode, photocathode, and consists of photoemissive cathode, a cathode which emits electron when struck by photons of radiation, several diodes which emit several electrons for each electron striking them, and anode. Photomultipliers have high sensitivity for UV and visible radiation and have fast response times. However, they are susceptible to damage when exposed to high intensity light. Photomultiplier tube is inherently more sensitive than photo. Now, next one is the ultraviolet or ultraviolet visible detector, that is the diode array detector, that is the multi-channel detector capable of simultaneous measurement of all wavelengths of dispersed radiation. So there is the end of silicon, there is the depletion range between a p-type of silicon we have to put up or bombarded the light source. It comprises of an array of silicon photodiodes on a single chip, generally 1024. The individual diodes are subsequently scanned for response. The diode array detector is less sensitive than the photomultiplier tube, but offers the advantages of simultaneous measurement of different wavelengths. Now, next, ultraviolet or visible light detector. UV detector are non-destructive chromatography detector that measures the amount of ultraviolet or visible light that is absorbed by components of a mixture being eluted of chromatography column. UV detector are often used as a detector for high performance liquid chromatography, that is the HPLC, ultra high performance liquid chromatography, that is the UPLC, UHPLC, nano flow HPLC, pre-preparative HPLC, process chromatography, fast protein liquid chromatography, FPLC, and flow reaction chemistry model. The detector based on ultraviolet absorptions are the most common detectors used for liquid chromatography. The ultraviolet or ultraviolet resistical valuable tool is used in various applications like as the pharmaceutical industry, biopharmaceutical, biotech, PET isotope research and production, food and beverage, oil and gas, adhesive, lubricants, detergents, cannabis, chem and marijuana potency and purification, research lab, quality control labs, quality assertion labs, fluorescent dye uses, photography. So these are the various applications for UV and UV visible. Now next one is the X-ray radiation. It is also known electromagnetic waves and their wavelength range is 0.012 in nanometer and their frequency range is 3 into 10 raised to 16 to 3 into 10 raised to 90. And their energy in the range 100 electron volt to the 100 kilo electron volt. X-ray have shorter wavelengths, higher energy than UV waves, and generally longer waves, lower energy than gamma rays. Sometimes X-ray are called Röntgen radiation after a William Röntgen, who is usually credited as their discoverer. Because X-ray have very high energy, they are known as ionizing radiation and can harm living tissue. A very high radiation does over a short amount of time causes radiation sickness, while lower doses can give an increased risk of radiation-induced cancer. X-ray are similar to gamma rays, however, the main difference is the way they are produced. The X-ray are broken into broad two categories. First one is the hard X-ray. So there is the energy is 5 to 10 kilovolt and wavelength is 0.2 to 0.1 nanometer. Hard X-ray are more usefully radiography because they pass through tissue. Due to their penetrating ability, hard X-ray are widely used to image the inside of objects. Example, in medical radiography, airport security. As a result, the term X-ray is metonymically used to refer to a radiographic image produced using this method. In addition to the method itself, since the wavelength of hard X-ray are similar to the size of atom, they are also useful for determining crystal structures by X-ray crystallography. By contrast, soft X-ray are easily absorbed in air and the attenuation length of 600 eV. It is equal to the 2 nanometer. X-ray in water is less than 1 micrometer. Soft X-ray with energy 100 eV to 5 kilo eV, that is the wavelength range 10 to 0.1 nanometer. It is the lower doses of a X-ray radiation can be very effectively used in a medical radiography and X-ray spectroscopy. In this case of medical radiography, the benefits of using X-ray for examination far outweighs the risk. In medical diagnostic application, the low energy soft X-ray are unwanted since they are totally absorbed by the body, increasing the radiation dose without contribution to the image. Hence, a thin metal sheets, often of aluminum, called an X-ray film, is usually spaced over the window of the X-ray tube, absorbing the low energy part in the spectrum. This is called hardening the beam since it shifts the center of the spectrum towards high energy or harder X-ray. Next concept is the difference between X-ray and gamma rays. It has the different parameters. First one is the origin. X-ray are emitted by electrons outside the nucleus. Wavelengths longer the gamma rays. Then frequency lower the gamma rays. Energy lower the and application medical diagnostic airports. And gamma rays, it is emitted by the nucleus. Wavelength shorter than X-ray. Frequency higher than X-ray. Energy higher than X-ray. It is used in a medical tracer, smoke detectors for house. So next concept is the sources, detector and application of X-ray. So sources are very fast electrons hitting a metal target, X-ray tube. Detectors are X-ray waves, photographic film, imaging detectors, photographic plates, image plate, flat panel detectors, spectrometers, X-ray crystallography, hybrid photon counting detectors, application image bricks, defects in bones, hidden devices, medical radiography, airport security, determining crystal structure, computed tomography, X-ray crystallography, X-ray astronomy, X-ray fluorescence, industrial radiography, border control drug scanner, sonographs. So these are the various parameters of X-ray waves ready. Next concept is the production of X-ray. See the diagram how to X-ray generator using cathode, anode. Then the incoming electrons release the X-ray as the slow down in the target, breaking radiation. When electrons strike on a target, when electron rearrange with an atom, then X-ray are produced. X-ray are commonly produced in X-ray tubes by accelerating electrons through a potential difference and directing them onto a target material, that is the tungsten. In incoming electron may also collide with atom target, kicking out an electron or leaving a vacancy in one of the atom's electron shells. Another electron may fill the vacancy and in so doing release an X-ray photon of specific energy. A characteristics X-ray. The production of X-ray by cyclotron. A cyclotron is a device that accelerates electrons in an evacuated ring, often several tens of meters in diameter, steering them with magnets, manipulate the electron beam in a controlled way with the magnets can produce intense beam of X-ray. Cyclotron facilities are used for research purposes. Cyclotron radiation is emitted by charged particles traveling on a curved path, as would happen while moving through a magnetic field. Since the source of electromagnetic radiation is the acceleration of the charge, cyclotron radiation is an example. Electromagnetic radiation produced by centripetal acceleration, as opposed to bremsstrahlung, which is produced by tangential acceleration. The wavelength of radiation is a function of energy of the charged particle, the strength of the magnetic field bending the charged particles. The spectrum of the radiation is continuous and is characterized by its critical wave. Cyclotron radiation is organized. The beam is highly polarized. Most of the waves are oscillating in the same way, and collimated. Most of the waves are in the same direction. X-ray tube produce messy radiation that is completely unpolarized and may be focused only with great difficulty. A cyclotron source is like an X-ray laser, while an X-ray tube is like a X-ray fluid. Now, next one wave is a gamma ray waves. So, gamma rays are the highest energy of radiation and typically have energies greater than 100 kilo electron volt, frequency greater than 10 raised to 19 Hz, and wavelength is less than 10 picometers. Gamma rays from radioactive decay are defined as gamma rays no matter what their energy, so that there is no lower limit to gamma energy derived from radioactive decay. Gamma decay commonly produces energy of a few hundred kilo electron volt and almost always less than 100 mega electron volt. Gamma rays have characteristics identical to X-ray of the same frequency. They differ only in source. X-ray are emitted by definition by electrons outside the nucleus, while gamma rays are emitted by the nucleus. The gamma rays are emitted in nuclear processes during radioactive decay or in nuclear reaction. When a nucleus in excited energy level goes back to ground level, it releases energy in form of gamma rays. The gamma ray detectors measure electromagnetic radiation through the process of the counting and measuring the energy of individual photons emitted from gamma ray detector measures electromagnetic radiation through a process of counting measuring the energy of individual photons emitted from elements. The measured energy of gamma rays corresponding to the type of elements and its isotopes, while the number of counts correspond to the abundance of the radioactive sources. Different types of detectors are used for detecting gamma rays. First one, simulation, which involves turning the energy of the gamma rays into visible light. And secondly, the solid state semiconductor, which creates electron hole pairs that converts the energy of gamma rays into electricity. So, gamma rays wave radiation, their sources, detector and application. First one is the sources, radioisotopes such as potassium-40, atmosphere interaction with cosmic ray particles, exotic astrophysical processes, mechanism of resampling, inverse Compton scattering, cycle of radiation, neutral coil decay, nuclear feature, photographic film, GF tube, simulation, solid state semiconductor. Applications are medical tracer, killing cancerous cells, sterilization of surgical equipment, refining, mining, chemicals, food, soaps, detergents, pulp, paper industries, for the measurement of levels, density and thickness. Now, next concept is the radiation and nuclear detector. The interaction of alpha, beta and gamma radiation with matter produce positively charged ion electrons. The radiation detector are devices that measure the ionization and produce an observable output. Early detector used photographic plate to detect tracks left by nuclear interaction. Advances in electronics, particularly the invention of the transistor, allowed the development of electronic detector. Cellulation type use vacuum tubes to perform the initial conversion of light to electrical pulses. The basic radiation detector system to know about the radiation like as energy, position, where did it come from, and how many and how much. So it is the block diagram of radiation and nuclear detector. There is the incoming radiation. It's detected by a detector converted into a signal like as a current or pulse signal that amplify by a analog circuit signal conditioning circuit. And again we have to use a ADC, that is the analog to digital converter, and which given to the disk and store, and which shows the numeric value of that radiation. The radiation or nuclear detector has some properties of radiation detector which depends on the application. First one is the energy resolution, second is the spatial resolution, third one is the sensitivity, fourth one is the counting. So detector operated in two ways. First one is the pulse mode, second one is the current mode. So pulse mode, it detects individual photons required for NM imaging application. Current mode, measure average rate of photon flux, avoid daytime losses. So types of radiation detector, so which depend on detection modes and functionality. So first one is the counter, their function is the number of interaction, mode is the pulse mode. Second one is the spectrometer, there is the number and energy of interaction, mode is the pulse mode. Third one is the dosimeters, it is net amount of energy dissipated, it is the current mode. And last one is the imaging system, that is the computed tomography, and that is CT scan, and nuclear medicine, that is the NM. So there is the two modes, that is for CT for current mode and NM nuclear medicine for pulse. So types of radiation or nuclear detectors. First one is the gas field detectors, second one is the solid state detector, third one is the organic cellularization like the liquid and plastic, and fourth one is the inorganic cellularization. So cellulator operates with a photosensors, photomultiplier tube, that is the another detector. So first one is the glass field detector. So it contains the three main parts. First one is the ionization chamber, second one is the proportional counter, and third one is the GM counter, GEIGER-MULLER counter. So it is used for continuous current output, pulse current output, pulse. So proportional counters and GM counter must have thin wire anode. Principle of gas field detector is a gas molecule get ionized when energetic charged particles propagated through a gas. A gas field detector consists of a volume of gas between two electrodes with an electrical potential difference voltage applied between the electrodes. Ionization radiation produce ion pairs in the gas. So first one is the GM counter. The detector most common to the public is the GEIGER-MULLER counter, commonly called as a GEIGER counter. GM counter principle: gas molecules get ionized when energetic charged particle propagated through a gas. It uses a gas filled tube with a central wire at high voltage to collect ionizing produced by incident radiation. The electrons produced by ionization, if accelerated by a high potential, can cause further ionization of gas molecules, thereby generating a large number of more electrons. It can detect alpha, beta, gamma radiation, although it cannot distinguish between them. Because of these and other limitations, it is the best used for demonstration or for a radiation environments. So that is the concept of a diagram of GM counter. It is a metal cylindrical field with lower pressure gas tube with a plastic or ceramic window at one end. The ionization particle passing through the tube ionizes in gas and electrons, so produced move towards anode. The velocity is quite high and they later produce secondary electrons after repeated collisions with the particles of the gas. These secondary electrons further produce more electrons in geometric progression due to this large multiplication action. A large ionization current is produced. The gas multiplication factor is so large that an avalanche dies in one point but spreads all over the entire length of the signal. Advantages and application: it can be count alpha, beta and gamma particles as well as cosmic ray. It has high sensitivity. Power supply need not to be partially regulated as the pulse height is constant over a large range. Because of the fact the output pulse is very high, so the amplification needed is also very subtle. Cheap detector with a large variety of size and application. Applications: particle detection of alpha, beta particles, gamma and X-ray detection, neutron detection. So next one is the solid state semiconductor detector works on the principle on gas field detectors, that is the production of electron hole pair in semiconductor material. Only up to 3 electron volt for ionization and up to 340 electron volt air. Usually needs to be cooled thermal ones. Cadmium zinc telluride detector can operate at room temperature. Usually requires a very high purity materials or introduction of compensating impurities that donate electrons to fill electron traps caused by other impurities. Silicon detector for X-ray up to 20 kilovolt. Germanium detector can be range less than 10 kilo electron volt to few mega electron volt. Such detectors have application in environmental radiation, trace element measurement. Germanium gamma rays detector plays the central role in nuclear high-speed physics, where gamma rays are used to measure rotation of neutron. The neutron detection is the effective detection of neutron entering a well-positioned detector. Neutrons are much harder to detect because they are not charged. They are detected by nuclear interaction that produce secondary charged particles. Boron trifluoride BF3 counter make use of the 10D and A7Li reaction to detect neutrons. Often one uses moderators such as paraffin to flow the neutrons and thus increase the detection efficiency. These detectors are used to characterize the energy spectrum and intensity of the neutron. Now, next detector is the sannulation detector. Sannulators are usually solids, although liquids or gases can be used, that give off light when radiation interacts with them. When high energy atomic radiation are incident on a surface coated with some fluorescent material, then flashes of lights are produced. Sannulator type detectors use vacuum tubes to perform the initial conversion of light to electrical pulses. The sannulation are detected with the help of a photomultiplier tube that gives rise to an equivalent electric pulse. The light is converted to electrical pulses that are processed by electronics and computer. Example: sodium iodide, that is the Ni, bismuth germaniate, that is the BgO. These materials are used for radiation monitoring in research and in medical imaging. Thank you.